He's interested in building and operating distributed systems. This talk will share experiences on how to match the demand of a machine resource and keep the costs low at the same time. So the topic of the talk is cost-effective autoscaling on AWS. A round of applause for our next speaker, please.
Me? Awesome. Hi, hello everyone. Hope you guys had a really nice lunch. It was really nice. Thanks to the organizers. So this talk is, I've changed the title a little bit to match with the actual content that's there. So these are some of the lessons that have learned managing Hadoop clusters on AWS while working as part of Index. So this talk is available online. That link, you can check it out and follow it if you want to along with this. Okay, so a little bit about me. I would like to call myself as a developer on ops duty. Working at Index, I was one of the first 5 engineers to join there, so I got a chance to work across the board, building systems, managing the systems, setting the infrastructure and all that. I contribute to OSS quite a lot. That's the link where you can find all my scrap code with Apache 2 license, and you can harass or contact me on Twitter using that handle. Okay, so there are some assumptions that I'm going to make in this talk that all of you are familiar with notions of AWS. Like there is what an AWS region means, what an AWS availability zone means, and also that you guys have heard or used spot instances before. Quick show of hands who haven't heard of spot instances before. Okay. Try to follow it along. If you have time, I'll probably do a quick primer so that you guys can catch up with the content. And if you guys have worked or operated Hadoop clusters, you might be able to appreciate some content. Well, it's just a hope. Okay, so the agenda goes like this. I have around 30 minutes, so I'll try to touch upon each of these topics around 10 minutes each. First is about our culture at Index and how do we do autoscaling as a problem, and how do we tackle cost reduction as another problem, right? So yeah, what's a talk that if you can't start off with a quote from one of the research papers? So the quote, this is a quote from a paper called On Designing and Deploying Internet Scale Services by a person named James Hamilton. He was part of the Windows Live platform team, and this paper got published in 2007. Like that's maybe 3 to 4 years, even before Netflix started launching their tools or their toolkits with Chaos Monkey and all that. This paper has lots and lots of beautiful content inside it. If you guys are really into operations, you guys should seriously check out this paper. So this particular quote is what our mantra is at Index when we work across anything in general, systems. If a development team is frequently called in the middle of the night, automation is most likely the outcome. If it's the operations teams that's called, the general reaction that you always get is to grow the operations team, or go buy that particular software, or just go get me that subscription, things like that. And we'll look into why that actually happens. So at Index, developers are responsible, apart from writing code, they're also responsible for infra provisioning, configuration management for those instances, deployment, like managing the releases across various test environments, and pushing it to production. Everything is automated. We use GoCD heavily, and all those things are one-click deployments or completely automated deployments. And also, developers are on-call roster. It's not the primary support for any system going down 3 a.m. in the morning is the developers, and not the operations people as part of the team. And this 4 principles sort of holds good for all the systems that they inherit and build. That's one of the key things, because sometimes it so happens in organizations you choose to use these fancy tools that's out there that has this tremendous amount of marketing and traction. But people have not even a slightest clue of what it means to take that system and run it on production. Right? They don't even know how the interaction happens or what are the components in there. Even without understanding, they follow a shell script where they do a curl, pipe it to sudo bash, and hey, my system is up and running, right? Things like that. When we start asking developers to take care of all these things, they think like, I don't know, maybe 3 or 100 times before they even come out with suggestions of bringing in new stack into the organization as part of the workflow. as while the developers do all that, the general question that people ask me is, what does your operations team do? So we sort of work on what is called as making our infrastructure human fault tolerant. So human fault tolerant considered as something where it's super hard to make a mistake, or if you have done a mistake, it's super easy to fix that, either using a revert mechanism or like you have proper backups in place where you can automatically roll over and fix those things. And Ops team also takes care of our AWS cost because we are completely on AWS, and being a startup, every single penny that we spend on an infrastructure that's not useful is going to hurt us back sometime in the future. And the ops team also takes care of some processes, like we have a thing called ops review, where we come up with a huge checklist for every system before it says it's live in production. You can bring up a production-like environment, test it, play around with it, do whatever it takes as a developer. But before you sort of acknowledge, hit the Kong and say, hey, my system is running in production, some person in the DevOps team has to sign off saying these follows our checklist for running the system or such a system on production. And apart from that, we also take care of other management of peripheral systems, like what are the tools for doing a configuration management, the logging infrastructure, the metric collection, the alerting, all those cross-cutting things across all the teams. Those sort of practices are taken care with the ops. So just to give you numbers, we have around 3 people in the ops team taking care or overlooking the work of the operations done by 50 plus developers across the board. So this talk, where I'm going to talk about these things, it so happened like around last year, same time, we had this problem where our cost was increasing and our systems weren't scaling enough. Index deals with a lot of product information, and this is one of the ripest time in the year where you have the holiday season coming in, the end of the year, the Christmas, the New Year. All those things add a lot of value to us, and our customers use our systems only to get information during this part of the year. And that's when we were struggling really hard last time on how do we scale our systems to match the demand and also sort of keep the cost under the tab so that we know what we are actually doing. So the whole talk is sort of, from this point, is split into two. One is the dev problem of how do you think autoscaling is a first-class concept in building any system, building or using any system. And the other part is about how do we keep a tab on cost, and what are some of the tools or techniques that we have figured out or learned over the last 10 to 12 months that I would like to share. And for giving concrete examples, I'll be talking both the autoscaling and the cost reduction from a notion of Hadoop clusters. But you can sort of replace Hadoop with any other system that's built internally or any other fancy system you find out there. It should, to an extent, sort of match. So the dev problem. So just to give you some context, we use Hadoop quite a lot. We have like at least 3 versions of Hadoop last time I checked, running for different use cases because teams are just too lazy to migrate their code base. And each clusters have different usage patterns. That's very common, right? Sometimes your staging or your pre-production might not be running 24/7, or you just want to quickly run an ad hoc job to do some data analysis, whereas your production workloads will be running, like, say, hundreds or thousands of jobs and running 24/7. That sort of holds good in our case as well. And so the way we sort of started handling these autoscaling problem is every time, so can you guys see the picture, the screenshot? So that's from one of our templates from our Go pipeline. So the first stage and the last stage would be like scale up the cluster before you actually start running your pipeline. And after the jobs are complete, scale down the MR cluster, right? It's a very simple thing that we started off with where it gave us a proven notion, and it's easy to reason about. Okay, I'm actually starting my cluster, I'm running a series of jobs, and then I'm scaling it down. This guy initially worked really well for us until these things happen. When a pipeline fails in between, when a particular job fails in a pipeline, Go wouldn't promote it to the next stage, so your cluster is not scaled down. It just keeps running in some white corner. Like your AWS bill keeps ticking on one end, but people hardly realize. And every time you start adding a new pipeline as part of our data pipeline flow, you got to copy paste that job configuration. Okay, this is the beginning, the first stage where you scale up, and next is the scale down. Third one is a classic case of, I mean, it's like so far we were on 1980s where it was a single-threaded system, and now you go to multi-threaded where you have these semaphores and all those things coming in. When you have two pipelines working on the same shared cluster, things really starts getting messed up. Where one guy would run to a completion and scale down, where the other guy would be running in between or in the middle, and this job would fail for no apparent reason. And people would like come up and realize, and like there's nothing wrong in the logs, and everything says the tasks are killed, and you start wondering why. This sort of hit us really bad. I mean, it has bitten us really bad bunch of times. So that's some to set some context. So this is sort of how we started off our Hadoop journey, where we have, I mean, for this, I'm going to consider MapReduce Hadoop 1 notion, not the Yarn 2 version of it. So you have one job tracker or name node running, and then you have a bunch of task trackers and data nodes running along, right? This is typically how you would set up a Hadoop cluster. And then you start realizing it's very difficult to scale up or down, because every time you want to add a new node or delete a new node, or if one of the nodes go down, you have to constantly keep adding a new one. And then you replace the whole individual instances with an auto-scaling group, so it's easy to scale up and down using policies or whatnot, right? Auto-scaling group opens up a completely new perspective to the whole thing. And I mean, these are some of the really good parts. So Amazon Autoscaling Group, I mean, in my personal opinion, it's one of the best products created by AWS after S3. So the guy really scales to really large number of instances. It has cool-off capabilities. You can, like, to avoid scale storms, just because you have a sudden spike, it wouldn't automatically scale up and down like your graph, but it can keep your cluster up and running even if the demand isn't very high. And after only a point in time, it starts to scale down if there isn't any demand continuously for a period of time. It can also sort of auto-balance your instances across different subnets or availability zones if your subnets are across different AZs. And it has first-class integration with ELB if you're on AWS. So there are past solutions like Beanstalk also sort of comes, you get to support these systems as well if you're using Elastic Beanstalk. But the limitations are purely with regard to how you can work with the auto-scaling, that it can only support one active launch configuration at any point in time, which means you can only have one instance type running at any point in time in your cluster. I mean, it's more like it's not at any point. You can have different instances with different LC configurations, but the active one is what is used for any new instance that are coming up. It's very difficult to map, or you can't write any complex logic if you want to say, I want these many numbers of C3 and this much number of M3 instances and things like that. And also, those instances have to be of a single life cycle, an instance life cycle that is they can either be completely spot or they can be completely on demand. You can't, again, mix and match a percentage or all these fancy things you get with these modern load balancers. You don't get those features. And also, autoscaling group supports autoscaling, like real autoscaling, with using your metrics. But the problem is it's tightly coupled with CloudWatch. This was sort of a deal breaker for us because we weren't using CloudWatch, and we had our own in-house setup of influx-based metric collection system we had, and we just couldn't do anything with it because it's very hard to integrate with that. And the other problem with using CloudWatch-based metrics is you get to choose only one alarm for scale up, and that can only be based on a single metric. If you want to combine or do something based on multiple metrics, you do the custom, whatever calculations you want, and you emit that as a single metric and decide to scale up or down based on that. So to solve all this problem, we built a tool internally called Vamana, which sort of does application-specific autoscaling. So this is sort of a general workflow of Vamana, where you have an application pushing demand and supply metrics. This is one of the revelations when I started working on this. So any autoscaling in general, the problem can be viewed as a demand and supply, where your demand is how much resources you need, either in terms of compute or storage or whatever, any network capacity, how much ever you want. And supply is what you already have. Your autoscaler's job is to make sure it tries to match them always using some external factors. So we push all these metrics to a store, and Vamana sort of runs in a cron, gets all these metrics, does some computation, custom computation, and then sets the desired value on the autoscaling group at any point in time to decide, okay, this is the current number of instances you should have in your cluster. So applying the same notion for Hadoop, we started off collecting the supply and demand metrics as how many mappers you have and how many reducers you have, and we sort of push them into a particular store. Actually, there are some links in the notes. If you can check it out. We have a sample Python code that pushes these metrics to CloudWatch to get, if you guys want to quickly try out on all of this. And once we sort of built this, put it onto one of our staging setup, we started seeing immediate cost reductions, which was not the original goal of the whole exercise, but came out as a pretty good coincidence. This is on like, I guess, 10 or 15 node cluster, having very low usage. We immediately started seeing there was around a $30 saving per day on this one particular cluster. So, I mean, the whole thing is, so far we talked about a happy consequence, but the real problem of autoscaling is one of the core strengths of Vamana, in my opinion, because Vamana is sort of built in a very generic fashion where you can choose to say, how am I supposed to scale up this application? If you take any autoscalers that are out there, they would take a bunch of metrics and most likely, I think I just checked out the Kubernetes documentation. Their autoscaler supports only on the target CPU utilization. If your utilization is 50% or more, the replication controller spins up another pod and then you horizontally scale. But sometimes you don't actually max out on CPU. When you talk about Hadoop, it's the number of tasks that you have. And the tasks and your CPUs might not always correlate. If you're doing very data intensive work and not, which are mostly IO bound and not compute bound, your CPU wouldn't spike out. Right? Your CPU would still be like around 30% or 40%, but your network throughput or all other metrics would shoot out of the roof. Or if you take other cases of Mesos, for example, the way Mesos works is it gives an offer to the underlying framework. Right? You can't request something from Mesos, you can only accept an offer. Now in that case, that is really very hard to say from a Mesos perspective if I have enough infrastructure for my underlying resource. So different use cases have different purposes. That's where Vamana kicks in, because you can plug it in for any kind of application you want, right? And okay, the black thing is supposed to represent a scheduled autoscaling, where if you know, okay, at this point in time on this week for this many days, I'm going to have my production pipeline running, I might as well just scale up blindly. I don't even have to look into the metrics because I know it's a fixed time schedule. And it's a proven pattern. If you know it's a proven pattern, you can sort of hook into that as well. And you can plug in any metric store. CloudWatch or Influx or, I don't know, Graphite or whatever you guys are using, any existing system, Datadog, for example, you can plug that in and you can have providers to build it out. And autoscalers are also pluggable, because just like how you can plug everything else, you can also plug in other custom autoscalers, not just Amazon's autoscaling group, but if you're running systems on Marathon and you want your application to scale up, you can do that. If you're running things on Kubernetes where you realize application metrics says it to scale up, but your system metrics or pod metrics does not yet guarantee an autoscaling, you can manually go set the number of pods you want in the replication controller and scale up. Right? So this is sort of how Vamana is built. Okay, all these are fancy talk. Okay, sorry to break it out to you. The real implement or the open source implementation that we have out there supports a very native version of Hadoop and CloudWatch integration and autoscaling group integration. We have, I mean, the internal code or the internal copy of the repo. We have support for Marathon. We have support for GoCD autoscaling and all that. We are on the progress of trying to push it to the open and get some feedback. So yeah, that's just to set the expectations right. Okay. So next is about the ops problem. Now, we talked about how do we scale systems, right? Okay, maybe I should talk about this. One of the things this sort of guarantees are, it set the mindset in the developers of Index is people started thinking autoscaling as a first-class citizen for any system you bring into the table. It could be systems that you build internally, or it could be the systems that you try to bring in from the open source world or anywhere else outside. You start thinking, can this system scale? can I sort of, can the system handle if the demand is going to increase? It could be whatever could be the demand. It could be the number of jobs you run. It could be the traffic from the external world, whatever it is. How do you start thinking of autoscaling as a first-class notion? Vamana sort of set a benchmark for everybody to catch up on. And in one of the points in the ops review is also to make sure, okay, how easy or difficult is it to integrate our autoscaling solution Vamana into your system or into this system that you're trying to push into production, right? So those are the takeaways from this part. The next is, okay, when all these systems scale, right, the other part that comes in is the cost. Because though cloud enables you to scale elastically, that's the promise of the cloud, the whole notion doesn't come free of cost. Or it comes with a huge cost. It's very hard to just see it upfront. So we started using Spot instances for our Hadoop clusters some time back. And we ran into a bunch of issues. I'm pretty sure folks who have used Spot instances would also agree with me. I'll walk you through what are the things that we saw. Okay, so first thing, so this is how our Hadoop setup was. That's the traditional setup that I showed before, with Vamana taking care of scaling up the autoscaling group based on these demands and metrics. Now, the first problem with this guy is any instance that you spin up by default in an autoscaling group is an on-demand instance. What that means is you pay only on an hourly basis on how much of the instances you use. To give you some numbers, if you're running, say, an M3.2XL, it's one of the instance type on AWS that has like 30 gig RAM and 8 vCPUs, as they call it. You would be charged around $53 an hour. And for a day, that's 1,200, and that number, $1,200 plus dollars. For running it over a month, you pay $36,000. For a production workload in our use case where you had to have it running 24/7 across the entire month, this came out as a separate, when we started tagging the instances and seeing in our bill, there were these production clusters standing right on the top saying, you know what, I'm the largest consumers or factors of your AWS bill. And that's the first problem we had in our initial architecture, or when we started working with Hadoop and AWS, the cost of on-demand instances. So what we did was, that's when we heard about the Spot, and we said, okay, let's use Spot instances. And Spot instances are really cool because they give you the best value for money, but they come at a cost. It's like a huge risk and a reward, where the reward is you only have to pay 10 to 20% on an average. It's not like a fixed thing. On an average, you pay only around 10 to 20% of the OD cost. That is, you get 80 to 90% savings on your traditional bill. But the catch is Amazon can pull the plug out of your instances anytime. Right? That's the whole thing. I think around last year, they launched this new feature called termination notice, where they give you like 120 seconds heads up that I'm going to pull the plug on your instance. But it's still not that useful in our use cases because not all apps that you run are AWS aware. Like in this case, Hadoop, for example, right? What do we do? So that's the second problem, Spot outages. How do we deal with Spot outages? So folks who know Spot instances, there are two options. One is you can switch to a different instance type, so that because the Spot variability is with regard to a specific instance type, and it's generally the promise is it doesn't affect other instance type. So you can sort of move to a different instance type to change it. The other thing you can do is you can sort of split your instances across availability zones, because your Spot market also differs on different availability zones. If a US East 1A has huge demand, US East 1D may or may not have the demand. There is no direct correlation, but it can also affect because people start migrating from one AZ to another. You will start seeing this AZ also going up, but it's generally, there's no theory or proven thing that it affects it. Right? So the thing that we started off is we couldn't use a different instance type because of the LCE problem, where you can only have one particular instance type in your cluster for an autoscaling group. So we didn't go with that approach. We went to the other approach where we split the clusters into different AZs. We had quite a bit of success with that for some time until we saw the data transfer section of our AWS bill started increasing. Right, so AWS, whoever came up with the billing strategies in AWS is a genius. So any single solution you try to move from one thing to another, they have a class that can start charging you for that. So we started seeing our data transfer section started slowly growing up, and we were wondering why, and realized for systems like Hadoop where you run HDFS, the right pipeline with, say, replication factor of n. So whenever one of the nodes goes down on one AZ, HDFS immediately starts replicating to the others that are there within the cluster so far. Now, that transfer happens so that you initially pay the cost of writing the data in the first place. Now, when you lose an instance, you pay the cost of started replicating the data in the second. That's in the second part, right? And it's not just the HDFS. If you're running traditional MR, your reducers would download the mapper outputs over HTTP. Now, if those mappers ran on a task trackers on a different AZ, you still start charging, they would still start charging you for the data transfer cost. So it's like, you have to pay. There's no going back. So that's the third problem, data transfer cost. And this is when it sort of realized, it's stuck hard. Go back to the single AZ. There's nothing else you can do, because if you are going to move your bytes across the wire to a different data center, Amazon is going to charge you. Like, you really can't do anything about it. But this time, find a way around spot outages that happen within a single AZ. So at this point, virtually we had, not like virtually, literally we had only one option, that is to move across the instance type if you want to stick with a single AZ, right? But we came up with something different, which we'll look into it. So the learning so far is you need a fleet of a system that could be like, say, a Hadoop 1 or a Mesos, a Yarn, any distributed systems that span across instances running 24/7. Right? If you're not running 24/7, you're better off using services like EMR or any other setup which is going to provide you like you pay an extra cost for the amount of duration you use apart from the instance cost, but that's okay because you're going to run, your usage pattern is very limited, and paying that small extra amount for the operations is totally worth it. If you're companies like us, where you want to take control of your infrastructure and you want to save cost also at the same time, running these managed services is useful, but at some point they're going to come back, and instead of paying to AWS, you start paying to these guys. Or your bill sort of now splits into two, where you pay some portion of your original amount to these guys, and the remaining part still goes to AWS, right? So that's the 24/7 is one of the important thing. The next part is based on our learnings, you can't use on-demand instances. You want to use pod instances so that you can save cost. And you also want to handle surge pricing for these pod instances. The approach we took there is, let's switch AZs. When a particular AZ for an instance type is having a surge, let's move to a different AZ altogether so that we can handle it. That was our genius way of handling the situation. Not something that I'm proud of at this time, but yeah, this is what we could come up with last year. And we also had this interesting use case where we want to fall back to on-demand because, on-demand instances. What that means is sometimes your spot instances go beyond the on-demand prices. I never really understood why that ever happens, but sometimes for an M2.2x large, where we saw it was 0.53, people are willing to pay $5 an hour. I don't know why, but sometimes people have money and they can burn, so they pay AWS all that money. So at those points is when we realized, it's better off where if you fall back to on-demand, rather than trying to battle these algorithmic pricings on the spot market. So we also wanted a use case where we could fall back to an on-demand basis for some time and switch back to spot once the surge ends. So we still continue to save cost, but we also have, moving to on-demand gives you the upper, a notion of what is the maximum amount of money you will ever pay for a cluster, right? It gives you an upper bound for that. And that's really useful for the finance folks if you are working with them. So to handle this, we built another tool internally called Matsya, which optimizes for cost and keeps the fleet running. So this is also written in Scala. So it sort of monitors the spot prices and moves the autoscaling group to the cheapest AZ. is meant to run as a cron on, say, a master instance. And we also wanted some notifications when it posts a notification to Slack whenever it's migrating the cluster from one AZ to another. So yeah, how does Matsya work? You have these systems that you want to run. You're going to typically put them on an autoscaling group. To save cost, that's going to be a spot autoscaling group. And you have all these different regions or availability zones across different regions available. What Matsya does is to place this particular autoscaling group on the right AZ so that you can have the best value for the money. And sometimes you also have the approach we took is we have an on-demand autoscaling group where we sort of switch the autoscaling value from this guy to another if you want to fall back to on-demand. And after a fixed duration, like say, I think we have 50 minutes, after which we try to see if the surge ends on these instance type and sort of move it back. So that's essentially all Matsya does. So we have this running for around 10 months in our production systems. Along with Vamana, both Matsya and Vamana together sort of helped us reduce 40% of our AWS bill because we started shutting down machines that we don't use, and we started using spot instances that also directly resulted in decrease of the AWS bill for us. And because of these, we also have 50% of our total AWS infrastructure on Spot and 100% of our Hadoop MR workloads on Spot. I mean, the 50% is because 50% of our infrastructure is Hadoop. So that's why you have that 50% of our total AWS on Spot, right? I thought it was a really nice marketing gimmick if I'm going to put it there. So that's about Matsya. So our Hadoop setup on different clusters looks something like this, where you have the job tracker and the autoscaling group, but the autoscaling group can move between, say, US East 1A on the left and US East 1B on the right. So the arrows sort of have different colors, right? They represent, well, they're supposed to represent AZs. And Matsya takes care of moving them across different AZs, and Vamana takes care of scaling them up and down based on the demand and supply. Okay, so the key takeaways are, first one, make operations approachable to developers. I mean, most of these tools were made possible because developers took charge of the operations and realized, you know what, this is something we need to solve. Else, the approach that we were trying to solve earlier was, okay, is there any service provider who can solve this for us? Or is there something else we could do to, like, all possible hacks using Python, shell, and all that, whatnot. So you start bringing developers into the scene and give him an operations problem. See, this is a problem. Without this, you really can't go forward. How do you solve it? And developers really can come out to think and solve these problems. So that's one of the key takeaways for us. And I hope it works for you guys as well. Systems like Vamana sort of helped us to put autoscaling as a first-class citizen in checking out our checklist for any system that goes into production. And if you're using AWS, use spot instances. You can save really tons of money with that. But be cognizant of when to use it, where do you use it, and how do you use it, right? That's about it. Thank you. So if you guys have any questions, comments, feedback, please be gentle. If you want something else, we can sort of take it offline. But if there are any general questions, please let me know.
Here. Yeah. I saw that you had a need to run 24/7, right? So what are your thoughts on reserved instances? Why you didn't try?
Reserved instances, you still pay all those savings the reserved instances gives you, right, are with regard to on-demand instances. You probably get to save like, I don't know, 20%, 30%. Well, Spot was really, intriguing where you get to save 80 to 90%. That's the whole reason we didn't go with RIs. And that's one. The other thing is we didn't know we would be running with this sort of a cluster configuration for more than a year. Right? We started off using C3.2x large last year when we built this Matsya and Vamana. But now we don't use C3.2xl anymore because our workloads have changed. They are more memory bound now rather than being a CPU bound. Or I can still handle with 8 CPUs, but I need, we were using C3.2XL, which gave me 8 cores, but 15 gig. And we realized it's not cutting it out anymore. We need 30 gig of RAM. So we moved from C3 to M3 family. But my arrays would have become invalid by now if I had gone with that approach. Those are one of the two primary reasons we didn't go with arrays. But we do go with arrays for other stateful services. If you're running databases or persistent HDFS clusters, we do go with arrays for them, just not for these computes.
Okay. And one follow-up question. From your experience, right, is there anything that could have been done inside the AWS autoscaling itself, which could have allowed you to do more things?
I mean, last time I checked, last time is around 5-6 months back. If they could start supporting multiple metrics, right, they sort of beat Vamana hands down. The only reason I would ever go with Vamana over existing autoscaling group is because it gives me a notion of multiple metrics and I can plug in my metric policies. But compared to something where I have to start from scratch and store these metrics elsewhere. And the other thing is, I don't know if it still holds good, but the CloudWatch only supports 14 days of history. I don't know if they've changed it ever, or is it still the case? I stopped following CloudWatch quite some time back. Those are some of the two things. And it will be also cool if they could support other metric systems rather than just the CloudWatch, because they call themselves as infrastructure as a provider, but act like a platform as a service. Yeah. Okay. So do I have 2 more minutes, Abhishek?
Sure.
Okay. Can I get the presentation screen back? No, it's not. Sorry? Okay, so this is for folks who haven't used Spot instances before. Just want to do a quick 2-minute primer. So AWS leases unused hardware. Like, unlike the service part of the AWS, where they promise you elasticity, you can add more instances when you want, underlying they are still bare metals, and they run data centers. Now, they can't add machines like using a magic wand from Harry Potter to bring up a new servers and start handling your request, right? So they would over-provision their data center always. But sometimes you don't have enough need to use all those services, all those machines. So they sort of lease unused hardware at a lower cost. And that's sort of marketed, and they actually built a product out of it called Spot Instances, and which is what they sell. But the thing is, Spot Instances, because you get the same capacity as an on-demand instance, but at a cheaper rate. There is a huge fight for that. So the prices are very volatile, but highly cost-effective that we talked about if you're using right. And the other part is the whole demand and supply or the price fluctuations. The volatility of the spot prices are very local to its spot market. So what a spot market is nothing but, if you're planning to run a cluster, right, you could choose one of the many instance types that Amazon has. And you could launch those instance types on any of the availability zones in any of the regions. Now, for your use case, take an example, say I need an instance that has 36 CPUs, right? You have 2 instance type choices. That is, you can use a D2 to 8x large or a C4 8x large. Now, these 2 instances are available across different AZs on different regions. You take a Cartesian product of all the 3. You guys understand what Cartesian product is, right? Okay, thank you. You just basically multiply all those values, how many ever numbers you get, and then that's the total number of spot markets you have. You can effectively move your instance or your cluster across any of these spot markets if you have enough automation. So that's about the whole thing about spot markets and spot instances in general. Okay. Thank you, folks.
Thanks, Ashwanth. So we have seen that in past 2 days, our main themes have been around kind of you would have heard Docker and Kubernetes a lot. So how much public containers are.